I'm Anil Kumar. Welcome to my series on calculus. We'll discuss critical numbers in this particular video. Here are 4 questions. Question number 1 is, let f of x equal to x minus 5 times x plus 1. Find the critical points of f of x. Normally, we refer to critical numbers only. That means we are looking for the derivative of the function to be 0 or undefined. And we want to find the value of x. So that value of x is the critical number. When we say critical point, you have to list the value of y also, right? So that's the difference. So first question, you have to find the critical points. That means both x and y value. At x equals to 0, second derivative will be negative, positive or 0 for the given function. Question number 2 is, let the first derivative be equal to x squared plus 1 times x minus 5 times x plus 2. What type of critical point is located at x equals to 5? Question number 3. Let the first derivative be x minus 5 times x plus 2 whole square. For what value of x will the graph of f of x have local minimum? And in question number 4, we are going to analyze the second derivative. Equation for the second derivative is given to you. Write the interval where the graph of the function will be concave down. List the values of x for which the graph of f of x will have point of inflection. And part C is, if the derivative of this function is 0 at x equals to minus 1.5, 0 and 5, then what type of critical point is each? Explain your answer. Now in this exercise, since we are given the equation, you need to sketch the graph and then analyze to find the answers. You can always pause this video, copy these questions, answer, and then look into my suggestions. Now, let's answer them one by one. Question number 1. We are given a parabola, right? The function is a parabola. X minus 5 times x plus 1. You can easily sketch this function. It has zeros at 5 and minus 1, so something like this. Okay. So the zeros are at, let's say this is 5 and that is minus 1. So these are the zeros. So the critical point is where the derivative is 0. So it's very important to understand the critical point, or sometimes we say number, is when the derivative is equal to 0, right? Not at these x-intercepts. So if you are answering minus 1 and 5 in this case, it would be a wrong answer. So basically, in this particular case, it would be right in the center, the average value, where the graph turns, which will be, for this example, you can add these two, right? And then divide by 2. So when you add 5 and minus 1 divided by 2, you get the value as 2. So at x equals to 2, you have a critical point, the turning point, right? And you can find the value of this function at 2 by substituting it here. We get 2 minus 5 times 2 plus 1, which gives us minus 3 times 3, or minus 9. And therefore, the critical point for us in this case will be 2 minus 9, right? So this we did without derivatives. Now let us see how to find this with derivatives. We are given the function f of x as x minus 5 times x plus 1. You could expand this. You could also apply the product rule. Expanding, we get x squared plus x minus 5x minus 5, which is x squared minus 4x minus 5. That's the function, right? The derivative of this function is 2x minus 4. Now, for critical point, that should be equal to 0. Now, this function is 0. It means 2x equals to 4 or x equals to 4 over 2, which is 2, right? So we get the same answer as we mentioned here. To find the point, you have to substitute 2 and get the value, and therefore we get the value as 2 minus 9, right? So this will be minus 9. So that is how you find the critical point. So first part we have done. Find the critical points. There's only one point here which is critical, and that is at x equals to 2, the y value is minus 9, and this all actually represents a local minima. In this case, you can say absolute minimum value also, right? For a parabola, it does give you absolute minimum value of the function. Is that clear to you, right? So that is the part A of our question. So some of you can also sketch the graph and get the answer, but the correct method will be to find the first derivative and then find the critical point. Now let us answer part B, which is at x equals to 0, f second derivative will be negative, positive or 0. So for part B, we know the graph is concave up. Since it is concave up, the second derivative should always be positive. So at 0 also, it is going to be positive. So in this case, the correct answer is that the second derivative will be positive. Is that clear to you? So that is how we are going to answer the first question. Let's move on and take question number 2. This time we are given the first derivative. So let the first derivative be equal to x squared plus 1 times x minus 5 times x plus 2. What type of critical point is located at x equals to 5? Now to visualize, let us sketch this graph also and then answer. We have this time x squared plus 1 is not a 0, right? That's the imaginary 0. Now here we have at 5 and minus 2. So we have two zeros, real zeros I should say, at minus 2 and at 5. Graph is degree 4. So if you want to sketch this graph, it will be kind of a positive leading coefficient. So something like this, and then here like this, and then going up, right? So this point is at minus 1, kind of, right? So it's an imaginary root. So that will be the shape of the graph. Now, what type of critical point is located at x equals to 5? Now this derivative is actually derivative of is the graph of the derivative, right? So there are two critical points here. One is at minus 2, the other one is at 5. What is this representing at x equals to 5? Now we know let us see at x equals to 5 what is happening. Before x equals to 5, it is negative, right? So it is negative, and after 5, the derivative is positive. So clearly, we have a local minimum at x equals to 5. Do you understand? Since the derivative changes from negative to positive. Since the derivative changes from negative to positive value. Is that clear to you, right? So that is how we figure out that it represents a local minimum. Correct? Now let's look into question number 3. Here again, we are given the derivative of the function. If f dash x is x minus 5 times x plus 2 whole square, for what value of x will the graph of f of x have local minimum, right? So let's again sketch this graph and then find the answer. Now most of the time you will see these questions in multiple choice with the graph, not the equation. Now I've added the equation to add the complexity. So we have a double zero at minus 2 and a linear 0 at 5 in this particular case. So leading coefficient positive, it is degree 3. So it's going to end up in this quadrant, correct? So at minus 2, the graph reflects and then comes back and kind of goes like this. Do you see that? So that becomes the graph of our derivative, right? F prime, so it's the derivative. Now, the question is, for what value of x will the graph of x will have a local minimum? So when we say local minimum, what do we want? We want the derivative to change from negative to positive, right? Then we have a local minimum, right? So that means from negative to positive, when it changes, we have a local minimum. Now, where does it change from negative to positive? Never, right? It is changing from positive to negative. So therefore, we have no local minimum in this case. Is that clear? So at this point, it is actually changing from positive to negative. So we have local maxima, not a minimum, right? Now here, the concave, this derivative is positive on both the sides. So it's neither minimum nor maximum. Do you see that? So in this particular situation, we do not have local minimum. Is that clear to you? Now, let's take the last example, which is to analyze the second derivative. So I'd like you to pause the video, copy this question, do it yourself, and then look into my suggestions. Question number 4 is, the second derivative is given to us, and that is x plus 1 times x minus 5 times x plus 2 whole square. Now, it's better to sketch this and then we'll discuss the options. Zeros are at x equals to minus 1. These are the critical numbers, x equals to 5 and x equals to minus 2, right? Okay. So we have at let's say minus 2, minus 1, and let's say this is 5. Now it's degree 4, right? And this multiplicity at minus 2 is of 2. So the graph will turn at this point, right? So it's linear otherwise. So the graph will be kind of like this. And this is the graph of second derivative, okay? Now once we have the graph, it is easier to answer these questions. A, write the interval where the graph of function f of x will be concave down. So we want f of x to be concave down, right? That basically means what? That means that the second derivative should be, you want concave down, which is like this, right? Concave down. So second derivative should be negative. Second derivative is negative in this interval, right? And therefore, the answer is when x is between minus 1 and 5. So that is the answer for A. Is that clear to you? Negative only in the interval from minus 1 to 5, and that is when the function will be concave down. Perfect? Now let's answer part B, which is list the values of x for which the graph of f of x will have a point of inflection. Now let's look for point of inflection. Now point of inflection is when concavity changes, right, on either side, right? Then we get point of inflection. Now if you look into the point, and also we need to have the critical number, that the second derivative is 0. So we are basically analyzing in this case the 3 points which are at minus 2, minus 1 and at 5. Now at minus 2 the concavity is not changing because positive, right? So it's concave up on both the sides, right? So it's concave up, this is concave up, that is concave down, and this is concave up. So we see that the concavity changes at 2 points. One is at x equals to minus 1, the other one is at x equals to 5. So these are the 2 points of inflection. Do you understand? So list the value of x for which the graph of f of x will have a point of inflection. So these are the 2 values where we'll have point of inflection. So we can write these 2 points as point of inflection. This is first point and that is the other point, since the concavity changes. Now, part C is if the first derivative, that is if f dash x is 0 at x equals to minus 1.5, x equals to 0 and at x equals to 5, then what type of critical point is each? Okay, so at minus 1.5, which is kind of here, right? Let's use a different ink. So at minus 1.5, we're looking at this point. So at minus 1.5, we have the second derivative as greater than 0, right? That means the graph is concave up, and therefore we have a local minimum, right? So at minus 1.5, we have local minimum, right? So this gives you local minimum. Clear? So at x equals to minus 1.5. The second point here is at x equals to 0. Now at x equals to 0, if we have this second derivative is negative. Here the second derivative is less than 0. That means the shape is kind of like this. So we have a local maximum. The third point here is at x equals to 5. So at x equals to 5, what happens? At x equals to 5, the second derivative is equal to 0. And therefore, we cannot decide about this, right? So x equals to 5, it is basically a point of inflection. As we can see, the concavity changes. So it's neither a maximum nor a minimum. Okay? So that is how you're going to answer this question. Perfect. So what we get from here is that we have a local minimum at x equals to minus 1.5, a local maximum at x equals to 0, and at x equals to 5 we have a point of inflection. So I hope with this the concept of interpreting the graph and the curves using first and second derivative is absolutely clear. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.